Welcome. If you're looking to get a quick, solid handle on some complex ideas in high-energy physics, you're in the right place. Today we're diving into how potential new physics, specifically through something called effective field theory, might, well, subtly change how particles we know, like the top quark, behave.
That's right. Think of effective field theory, or EFT, as a framework. It's a standard way we look for physics beyond our current standard model. Essentially, we add potential new ways particles could interact, described by new terms in our theory.
And we're zeroing in on a recent study that explored these subtle changes. They used top quark pair production at the Large Hadron Collider, the LHC, as a test case.
Exactly. The production of pairs of top quarks is a really well-studied process at the LHC, so it provides a good laboratory.
So our mission, let's say, for this deep dive, can these new physics interactions actually distort our measurements of fundamental particles? And what does that mean for experiments running now and the ones planned for the future? The sources we have are from research tackling this very question.
The core idea is pretty interesting. EFT introduces these new interactions, and they don't just exist on their own. They can interfere with the standard processes, the ones predicted by the standard model. This interference, it's like waves overlapping, can potentially change the measured shapes of particle resonances, things like the top quark or the W boson when they're produced and decay.
A resonance shape. Maybe think of it like the specific frequency profile where a particle resonates or is most likely to be found.
Precisely. And distortions to these shapes are what we're discussing. It's like adding a tiny, almost imperceptible waddle to a very familiar vibration pattern.
And why does this matter so much? Well, we need incredibly precise knowledge of how standard model particles behave. That's our baseline. If that baseline is subtly distorted by these EFT effects, it could make finding actual new physics signals much harder, like trying to spot a faint star next to a bright one.
It complicates the search, definitely. The specific study we're looking at focused on a particular type of new interaction, what are called four Fermion operators. These operators describe a potential new way for four fundamental particles, fermions, to interact directly. And in this case, they can affect both how top quarks are produced and how they decay.
Right, so the researchers asked, how might these specific four fermion interactions change the expected energy profile, the resonance shape, of the top quark? This shape is often described mathematically by something called a Breit-Wigner distribution. It's like the particle's energy fingerprint.
It is. And the fascinating part is that even if the new physics contribution itself is small and, say, constant across energies, the interference between it and the standard model process can actually tilt this Breit-Wigner shape. It's not necessarily making it taller or wider, but sort of skewing it slightly. A subtle asymmetry introduced by the interference.
Which brings us straight to the experimental side. The study really asks, are our current strategies, even at the upgraded high-luminosity LHC, sensitive enough? Can they pick up these very subtle, interference-driven distortions in the energy regions where we expect to see top quarks and W bosons?
To answer that, the analysis relies heavily on looking at differential distributions, things like the transverse momentum of particles or the invariant mass of decay products. These distributions give us detailed information beyond just counting events. They help reconstruct what actually happened in the collision, reconstructing the top quark events, for instance.
And they looked at one operator in particular, didn't they? Something called Q3LQ.
Yes, Q sub 3LQ. This one is particularly interesting because it can interfere directly with the W boson's role in the top quark decay. Since we often reconstruct top quarks by looking for that W boson signature, an interference here could distort the W resonance shape we rely on.
So what was the verdict for the LHC?
Well, the finding, at least for these specific four fermion interactions studied, is that the resulting resonance distortions are likely too small. Too subtle to be reliably picked out with the LHC's current experimental resolution and the amount of data, the statistical power we expect. And this holds true whether you look on shell, meaning right near the particle's mass, or off shell at somewhat higher energies. The effect just seems buried in the noise for the LHC.
Okay, so maybe not easily visible at the LHC, but the story doesn't end there, does it? The study also looked forward towards potential future colliders.
It did. Specifically, future lepton colliders, like the proposed Future Circular Collider, the FCCE, operating as an electron-positron machine. These machines are designed for incredible precision, potentially operating right near the energy threshold needed to produce top quark pairs.
And the thinking is, with higher precision, these subtle effects might become visible, like using a finer instrument to measure that wobble we mentioned.
Exactly. The study suggests that at a machine like the FCCE, with its much finer energy resolution, these resonance-shaped distortions could become much more pronounced, more measurable. This seems especially true if you look at observables related to the W boson decay products stemming from that Q3LQ operator's interference.
Is there a specific example they highlighted?
Yes, they pointed to the invariant mass distribution of the leptons coming from W boson decays. At the FCCE, the predicted change in the shape of this distribution due to the EFT interference is significantly larger than what's expected at the LHC.
So a clearer signal, potentially.
A clearer signal, yes, and they quantified this. The projected constraints on the EFT parameter, the strength of that new interaction linked to Q3LQ, are considerably tighter at the FCC compared to the LHC projections.
So let's try to wrap this up. It seems current LHC analyses are probably robust against these specific, subtle distortions from these 4 Fermi interactions. They likely won't mistake them for new discoveries just yet.
That appears to be the case based on this analysis.
But future precision machines, like an FCCE, could potentially turn these subtle effects into genuine probes. They offer a much better chance to see these distortions and really test these new physics ideas by looking closely at resonance shapes.
That's the main takeaway. This work really explored that fascinating interplay between potential subtle new physics and the precision measurements we make of particles we think we know well.
It highlights how the search evolves. While the LHC pushes the energy frontier, these future precision machines might probe physics in a different way, through extremely detailed measurements.
It underscores the need for ever more precise instruments to potentially uncover the universe's deeper secrets, which might be hiding in these subtle effects.
So the final thought for you, our listener. If even particles we understand as well as the top quark might have these hidden complexities, these subtle distortions, only revealable by future tech, well, what other surprises could be out there? Just beyond the reach of our current experiments. It's something to ponder about the ongoing quest in particle physics.